In this video, I'll talk about Maxwell's equations, and this is covered in chapter 34.2 and 34.3 of the textbook. Okay, so first thing we need to do is actually to rewrite Faraday's law in a slightly different form. So if you remember a couple chapters ago, we talked about Faraday's law, right? And we saw that a changing magnetic flux through some sort of a conducting loop is going to induce an EMF and hence a current. So, of course, more generally, even if you don't really have a conducting loop, you're still going to induce an electric field. So the EMF that gets induced, you can write as EMF is this closed path integral, this loop integral, E dot dl. So, and yes, this should look suspiciously similar to something we had for Ampere's law. But if that's how we write the EMF that gets induced, then we can rewrite Faraday's law that this closed path integral E dot dl equals minus d phi, the ddt of the magnetic flux. So this is just the more general version of Faraday's law that holds even when you don't have a conducting loop for the current to be induced in. So just a couple of quick comments. Of course, Lenz's law still works, so that tells you something about the direction of the induced electric field. Remember, the direction always opposes any changes in the magnetic flux. So, and the strategy then, and if you remember, Ampere's law had this closed loop integral B dot dl. For this new version of Faraday's law, it's the closed loop integral of E dot dl, so the problem solving strategy is actually pretty similar. Now, another interesting thing to note here is that these induced electric field lines have to be loops, right? We don't actually have any charges, and right, electric field lines they start on positive charges and end on negative charges. We don't actually have any electric charges, so our electric field lines must be closed loops, similar to what we have with magnetic field lines. Now, another interesting thing here is that the induced electric field is actually non-conservative, right? So if it's non-conservative, then you have to be careful and you can't define things like a potential energy for it. Now, however, probably the most interesting thing is that a changing magnetic flux is going to induce an electric field even in a vacuum. Okay, so now we're ready to write down Maxwell's equations. So all of electromagnetism can be summarized into 4 different equations known as Maxwell's equations. And these we're going to write in integral form. You can also write these in derivative form, but we're not going to look at that. So first off is Gauss's law for electricity. So the electric flux or through a closed surface, right, has to be proportional to the charge enclosed inside that surface. We had Gauss's law for magnetism, which says that the magnetic flux through a closed surface had to equal 0 since we don't have magnetic monopoles as far as we know. We have the newer version of Faraday's law. So, right, this closed path integral E dot dl is proportional to the change in magnetic flux. And the Ampere-Maxwell law that said the closed path integral B dot dl was proportional to the current through this loop, and we also had this term that had to add this term that depended on the changing electric flux. So these are the 4 Maxwell's equations, and actually it summarizes all of electromagnetism. And although there is one more equation that's important, and this is the Lorentz force law. So if you have electric and magnetic fields, the Lorentz force law tells you how to calculate the force on a charged particle. And it's just the charge, Q, times the electric field plus V cross B.